Good day, viewers. I am creating these videos to support teachers of maths in helping learners make sense of mathematical concepts and their associated procedures and processes. And today I want to look at the factorization of linear expressions. And I've got my algebra tiles here to help me because for factorization, my model for factorization is the same with algebra as it is with numbers. And if you've not looked at the video on factorizing with numbers or perhaps even prime factorization, then that might be a good place to start. So my model for factorizing with anything is, can you build me a rectangle with no gaps and no overlaps? So if we look at a simple linear expression, say for example, 6x plus 9, can you build me an expression with no gaps and no overlaps that has that uses these tiles, 6x plus 9? So here we have 6x, here we have 9. Can we build a rectangle, no gaps and no overlaps, that uses those tiles? Well, of course, I mean, the obvious thing we can do is to arrange those in one long, thin rectangle. So we can put the 6x's in one long, thin rectangle, and then we can put the 9 ones. But of course, this is just equivalent to saying that 6x plus 9 is one lot of 6x plus 9. It's 1 in width times by 6x plus 9 in length. And that's how we're sort of evaluating the factors of these rectangles, is what is the dimensions? What are the dimensions? What is the width? What is the length? Well, this is just a 1 by 6x plus 9 rectangle. So, okay, fine, not particularly useful in this case. And again, what we'll talk about with learners around this is actually making sure the rectangles has a width that's greater than 1, and then eventually we'll talk about having the width as large as possible, and we'll see that in a minute. So in this case, rather than that long thin rectangle, I can build this rectangle. And you can see that this rectangle uses all 6 x's and will, once I've finished dragging them in, use all 9 ones. And so then we can talk about, okay, well, what is the width and what is the length of this rectangle? And sometimes if I'm doing this on the screen, obviously pupils working with their tiles, but I'm doing this on the screen with them, I might drop in the horizontal and vertical so they can actually see, okay, so the width here is 3 and the length here is 2x plus 3. And so what we have here is the factorized form of this expression, which is not 2, getting ahead of myself, is 3 by and then 2x plus 3. And of course, I can start to look at things like, well, what if these 9s are not positive? What if they are negative? So what if I make this expression into 6x minus 9? So here is 6x minus 9. Again, some people are not keen on the idea of negative area, but it's perfectly possible to model it with the tiles, provided pupils have some understanding of multiplication of negative numbers. Well, I can see now that the only way I can make this negative 9 is to either flip these, but that would make the x's negative as well, or would be to flip these. So actually what I've got to do is flip these round. And this now keeps this 6x positive, but makes this negative 9. So in that case, 6x minus 9 would be 3 bracket 2x minus 3. And I can change different signs here. I mean, what's interesting is, okay, well, if I want to have everything negative, so negative 6x and negative 9, Well, then actually what's interesting here is there are a couple of different ways of doing that. I could keep this negative, but also make this negative and have 3 bracket negative 2x minus 3, or alternatively, I could keep all of these top bits positive and make these negative. And what that's showing us is that negative 6x minus 9 can be thought of as 3 lots of negative 2x minus 3, or potentially can be negative 3 2x plus 3. And it's a little unclear as to which of those would be seen as the correct, in inverted commas, factorization, because the very idea of factors and numerical factors isn't particularly well defined and useful when it comes to negative numbers. Is negative 3 a factor of 9? Well, if negative 3 is a factor of 9, then surely negative 1 has got to be a factor of 7. But then is 7 prime anymore if it's got factors of negative 1 and negative? It all gets a bit messy and a bit there when you get around negative numbers and factors. Factors, in a numerical sense, are best thought about and make most sense when they are thought about in relation to positive whole numbers. Okay? But we can sort of see that both of these look like they're right. And whether you say, well, because these still share a factor of negative 1, it's actually this one that we want. But then, is negative 1 a factor of negative 3? It all becomes a bit sort of blur. And then when we come into something like, let's say, 12x plus 8, where we have potentially different rectangles we could make without having a width of 1. So here is 12x plus 8. And I have built there, obviously, the full factorization of that, which is 3x plus 2. And I can show that with the horizontal and the vertical again. So I can have 4 and then 3x plus 2. But of course, what I could do here is chop this rectangle in half lengthways and move one length to the end. So rather than having that, I could have, if I put these ones out of the way for a minute, just to keep all my x's and ones together. I'm going to run out of room there, I think, but you can imagine if I had all my ones at the end there, then I would have 2, and then I would have 6x plus 4. So how do we decide what the correct factorization in that case is? Well, like I say, there's a couple of ways of looking at it. There's either to say biggest width possible, use the highest common factor for the width, assuming we are clear on what highest common factor means for something like 12x when it's used with a number. Or we could say, well, if we were to factorize it as 2 bracket 6x plus 4, then we can see that 6x and 4 still share a common factor. So what we're aiming for is to have this without a common factor left in the brackets. The expression in the brackets shouldn't have common factors left in the terms, and that would negate that and mean that actually the one we want is 4 bracket 3x plus 2. And whether you say, largest width possible, highest common factor for the width before you start, or whether you're saying, well, if the expression in the brackets has still got common factors between the terms or within the terms, then you need to be looking for a larger factor in the front, anything like that. will sort of take care of that potential problem. Okay, and it doesn't just have to be x's and numbers here. If I have my second variable, then I can have something like 6x plus 9y, and that works in exactly the same way. 6x plus 9y, and obviously not all of the physical packs of these manipulatives have the second variable tile in them. So you might, if you don't have the second variable tile, it might be that you can only do this sort of showing kids on the screen. But again, we can see that that still has a width of 3, but now the length is 2x plus 3y. And, we can make the link back to the first problem that I looked at there, can't we? That if the 9 has just become 9y, then the 3 is now just becoming 3y. And, as well as this, as well as going straight from the expanded form to the factorized form, what I could be doing here is drawing a picture, drawing a partial abstraction of what it is I'm building with my tiles. So I'm building a rectangle using my 6x's and my 9y's, but the way I'm building that is I'm building it in 2 parts. I'm building it with the 6x's together first of all, and the 9y's separately. And then I found that both of these smaller rectangles inside the bigger rectangle have a common width of 3, that this part of the larger rectangle has a length of 2x, and this part has a length of 3y. And this, of course, is tying together with potentially drawing similar pictures for expanding. So we get the same sort of pictures for expanding and factorizing. So that is my short video on factorizing linear expressions. As always, I'd like to say a big thank you to mathspot.com and its creator, Jonathan Hall, for the wonderful website, which has a multitude of things for maths teachers. You can see all the different sections along the bottom here. I've been using the manipulatives a lot to help with these videos, occasionally the tools as well, but you will find lots and lots of different things on that site. So if you've never been to have that site, I would strongly recommend you go and have a look. And if you are interested in using visuals and manipulatives to support your learners in making sense of mathematical concepts and their associated procedures and processes, then can I suggest you check out my website, which is visiblemaths.co.uk. And on there, amongst the many different links and bits you'll find on there, you'll find a link to the publisher of my book. My book is called Visible Maths, and the publisher is Crown House Publishing. And on their website, you can see some sample pages of the book, and if you feel like it will be useful, you can make an order. I will be producing these videos throughout lockdown, so if you have a particular concept or process or procedure that you think I'd like to see that modeled with the manipulatives, I'd like to see how you might explore that with learners with manipulatives, then please do get in touch and hopefully I'll be able to create it for you. Thank you very much for your kind attention.